Hi, this is Kate, and this is the second video for week/fortnight 7 of Math 23B. So now that we sort of know how to think about these sequences of functions, let's take a look at another example that's very interesting. We're going to define our sequence f sub k of x, our sequence of functions, where k is our index, as follows. Note that for x values less than 0, f sub k of x equals 0. For x values between 0 and 1 over k, f sub k of x is equal to kx. And for x greater than 1 over k, f sub k of x is equal to 1. Now the first key to really understanding these functions is to draw a couple of them. So put this video on pause, give it yourself a chance to maybe draw f sub 1 of this, f sub 2 of this sequence, and f sub 3 of the sequence. If you feel like you might need to do f sub 4 too, go ahead and do that. If you found that difficult, all you need to do is plug in 1 for k in the directions below to start with f sub 1. Know that for k less than 0, f sub 1 of x is going to be equal to 0. For x between 0 and now less than 1, right? Greater than 0, less than 1, f sub 1 is going to be equal to x, and then for x greater than 1, f sub 1 of x is going to be equal to 1. So what does that look like? It looks something like this. So there's f sub 1. It's 0 for x less than 0. It's equal to x between 0 and 1, and then it's equal to 1 thereafter. Now we plug in 2 everywhere we see a k. X less than 0, still equal to 0. Now from 0 to 1/2, f sub 2 of x is equal to 2x, and then for x greater than 1/2, f sub 2 of x is equal to 1. What does that look like? That's about as close as my artwork is going to get us. So that red one is f sub 2. Now let's try f sub 3, right? X less than 0, it's going to be equal to 0. Now x between 0 and 1/3, it's going to be equal to 3x. And for x greater than 1/3, it's going to be equal to 1. Try drawing that in. And you can see the pattern, right? Note that each of these f sub k's is a continuous function at x equals 0, right? It's a continuous function actually everywhere. But let's try and figure out what the limit of f sub k is. Okay? Well, the idea is that if you look at any particular x value, if it's less than 0, the function value will always be 0. If it's greater than 1, the function value will always be 1. If it's somewhere between 0 and 1, right, eventually the function value will become 1, it'll increase to 1, and then it will stay there as k is going to infinity, right? That plateau of function values at 1, that interval where that happens, is getting larger as k increases, right? F sub 4 is going to look something like this, and it'll just continue on. Note that if you pay attention to some x value, maybe here, maybe down here. Here's where the first function value was for f sub 1, here's where the second one was, the third one, and then by the fourth one it turned into 1, and it's going to stay there through the 5th, 6th, 7th, all the way up as k goes to infinity. So what does the limit function look like? Remember, we call the limit as k goes to infinity of f sub k of x, we call that f of x. Well, the limit function, right, is going to be 0. I'm going to draw the limit function on a separate axis because I just have too many things going on over here. All right, for the limit function, every single function value for x less than 0 is going to be 0. I think we can all agree on that based on how these functions are constructed. Then at 0, right, it's still going to equal 0. If we pay attention to this right here, right, f sub k of x is equal to kx. And at x equals 0, that's equal to 0 no matter what. And then for x greater than 1 over k, well, what's happening to that interval, right? As k goes to infinity, 1 over k is approaching 0. It never itself equals 0. But for everything that's greater than 1 over k, f sub k is equal to 1. So we have to pay attention to what the limit behavior is for the function values at every single x that is greater than 0, right? Because this interval gets smaller and smaller and smaller, and eventually in the limit, right, 0 is equal to the limit as k goes to infinity of 1 over k. So this little segment, the diagonal line portion of each of these continuous functions, disappears in the limit. It gets squeezed in. You can see it getting steeper and steeper and steeper as k gets greater and greater and greater. And in the limit, what we end up with is a discontinuity at x equals 0. The function value in the limit function is 0 at x equals 0, and then the second that you get greater than 0, it's equal to 1. Because for any x greater than 0, eventually the function value there will increase to 1 and then stay there for the rest of the functions in the sequence. So this light blue guy on the left here is our limit function, f of x. Here are some of the drawings of f1 through f4. Well, what's interesting here is we have a bunch of continuous functions who in their limit they approach a discontinuous function. Let's see what else we can deduce about their behavior. Well, what's very interesting is that these functions do not converge uniformly to the limit function, right? Turn back to your previous page to take a look at what uniform convergence means. That means that for any epsilon greater than 0, there's some index, big K, that says for every function after this in the sequence, we're going to be within epsilon of our limit function. Well, if we put a strip whose width was epsilon around our limit function, let's sort of visualize what that might look like. There we go. I tried to make it sort of a nice thin epsilon. But I want to point out to you that for every single k index, for every single function, no matter what k is in this sequence of functions, right, it's continuous. That means there has to be some path that goes from, sure, we're within epsilon of the limit function down here, but then if we're talking about a specific function in the sequence of functions, right, it's a continuous function. So there's going to be a moment where it jumps from here up, and right on that path of that continuous function, for every single k this happens. It might be a really steep jump, but sure enough, we're definitely going to move out of this epsilon band, right? So there's no big K where you say, okay, for all values of x, we're within epsilon of the limit function. The limit function here is 0 for x less than or equal to 0. It's 1 for x greater than 0. And it's true that for every value of x, eventually, point-wise, right, this converges to the limit function, but it's not uniform convergence. This doesn't happen sort of evenly across the entire interval. There's always going to be some values of x at any given k that are going to lie outside of these yellow bands here. So that's one thing that we can say about this particular sequence. The other thing that's very interesting is that for each individual function, right, it's continuous in the sense that we can choose an epsilon and a delta partnership that works at a particular point for that function. But there's no one-size-fits-all delta, right? It would be so cool if we could say, no matter what function you're talking about, at this particular x value, if you're within delta of this x, your function values will be within epsilon of each other, no matter which function f sub k you're talking about. That's equicontinuity, and this function does not have that quality. It is not equicontinuous. And so that's some new terminology for some of you. So looking at this function, we can say, the sequence of functions, I should say, we can say that it's a sequence of continuous functions whose limit function is discontinuous at x equals 0. We also can say that the sequence of functions does not converge uniformly to the limit function. We can also say that this sequence of functions is not equicontinuous at x equals 0. There's not a particular epsilon delta partnership that works for every single function in f sub k, in the sequence there. And why is that, right? The real issue is that if you look at the same delta bandwidth right here, right? Delta is is the tolerance, the variance, the distance you can move around for inputs. The problem is that as k goes to infinity, right, the slope on this side here is getting steeper and steeper and steeper. And so what's actually happening as k increases is that the function values are getting further and further apart over a shorter and shorter band. And so that's why the same delta epsilon partnership doesn't work across all of the different functions, because as k increases, as you're looking at higher and higher f sub k's in the index k, you're seeing larger and larger oscillations of the function over that interval delta near 0. So let's take a look again. Let's talk about continuity. We also talked about uniform continuity earlier in the year. Now there's, equicontinuity and uniform equicontinuity, like, so many things. So take a moment. We're going to review that right now. Continuity. What does that mean? We say that a particular function is continuous, and we say that it is continuous at a particular point. So we're talking about a single function, and we're talking about a single point in that function, and we say, okay, if you give me an epsilon greater than 0 for any epsilon greater than 0, right? An epsilon is a tolerance as far as how much the function values will move around. You can give me a corresponding delta that will say, okay, well, if I stay within delta of the inputs around this point, then the function values will stay within epsilon of each other at this particular point. Uniform continuity, or saying something is uniformly continuous, we're talking about a single function, and we say a single function is uniformly continuous. That means that given some epsilon, right, that is a range of epsilon around the function value at a particular point, there exists some delta such that if the inputs are within delta of each other, the function values are within epsilon of each other. And uniform continuity is special because this epsilon delta partnership works over the entire interval. It's not input specific, right? When we were talking about continuity, we were talking about continuity at a particular place. We were saying, okay, if you stay within delta of this input, the outputs will be within epsilon of each other. With uniform continuity, that delta epsilon partnership works not just at that one x location, it works at all of them across the entire interval. So continuous, you're talking about a single function. Uniformly continuous, you're also talking about a single function. Equicontinuous means we're talking about a sequence of functions. Sequence of functions is equicontinuous. We don't say that a single function is equicontinuous. We say that a single function is a member of an equicontinuous sequence of functions or set of functions. So when we say this sequence or this set of functions is equicontinuous, that means we're talking about all of them. And we're talking about the behavior of all of these functions for a particular x value. And what equicontinuous means is that if you stay within delta, as far as inputs go, of that particular input x value, then the function values will be within epsilon of each other. And not only does this work for one particular function in the sequence, it works for all of the functions in the sequence, but at this particular x value. And then uniformly equicontinuous is an adjective that we use to describe a sequence of functions as well. We say this sequence of functions is uniformly equicontinuous, and that means that if two input values are within delta of each other, the function values that are our outputs are going to be within epsilon of each other. This works for any epsilon. You can provide that delta. And not only does this work across all of the functions in the sequence, but it also works across the entire interval. It's not just x specific. So continuous is talking about a single function at a single point. Uniformly continuous is an epsilon delta partnership across an entire interval, but it's only talking about one function. Equicontinuous is talking about an epsilon delta partnership that works at a particular x value, but works for every single function in a sequence. And uniformly equicontinuous is clearly like the hardest to satisfy. That means that we're talking about an epsilon delta partnership that works for every single function in a sequence and for every single x on the interval. That's quite something. I usually use a dance partner's analogy to talk about continuous, uniformly continuous, equicontinuous, uniformly equicontinuous. The epsilon delta technical definitions are going to be in your course notes this week. But try to think of them and learn them. Sometimes this metaphor helps. Epsilon and delta are dance partners. They dance together. Clearly I'm a dancer. This is why I've decided to create this metaphor. When you're talking about a continuous function, this means that this epsilon delta partnership, they dance very nicely together at a very specific place on the dance floor to a very specific song. So they can dance in this place on the dance floor to this song. Perfect. Uniformly continuous. Well, what does that mean? Well, the epsilon delta partnership, the dance partnership works anywhere on the dance floor, but only to this specific song. Equicontinuous. The epsilon delta partnership. They dance well together for any song in the playlist, but only on this particular spot on the dance floor. And then uniformly equicontinuous means that you have a dance partnership of epsilon and delta that works anywhere on the dance floor to any song in the playlist. So the analogy there is that the epsilon delta partnership is the partners that dance together. X is their location on the dance floor, and the song is the function in the sequence, basically. So give that some time. Those definitions are very challenging to soak in, but they're very important for the first big proof of the week, which we'll talk about in the next video.